About induction motor, the rotating magnetic field, what we saw yesterday, how the resultant magnetic field given, which is going to induce a voltage in the rotor, IM rotor. In IM rotor, there will be a voltage induced in the, whether it is a squirrel cage motor or wound rotor. This magnetic field will create induce a voltage. Okay, because of that, the voltage will be. We know that the coil in the induction motor is short circuited. If you see here, because this is coil 1, I say C1, C2, C3. This is a three-phase. One end is, both the ends are short circuited. You can see that whether it is the cage rotor, squirrel cage rotor, or in wound rotor also, finally you can see that you are adding additional resistance apart from the coil resistance through slip ring. Finally, end is short circuited. This end also short circuited. So that means we are not supplying any voltage to the rotor of induction motor, whether squirrel cage or slip ring. Both the end of the rotor coils. You have single phase motors also, induction motor, but we will talk with three phase here, easy to understanding, but it can be extended to single phase also. So both the coil ends, all three coil ends are short circuited. Now, as I told you that since we are supplying a current here, voltage, we are supplying RGB three phase voltage, the current IR, IG, IB, so it creates as phi R, phi G, and phi B magnetic flux. Because of this, we are getting resultant magnetic phi R, correct? So depending upon what is the value of, that's what we saw yesterday, sinusoidally, this is itself, voltage, current, everything is varying sinusoidally with respect to time. So each phase. So resultant vector, we saw that magnetic flux created by stator is phi R. That's what we saw. This is going to cut the rotor coils. So rotor also, there's a voltage is induced. Okay. So once voltage is induced, we know that if there's a coil, you have a coil, and if the coil is short circuited, and if there's a magnetic flux, I say phi, there'll be a voltage induced. We say V induced. Because of magnetic flux, this is a time varying magnetic flux. If it is a constant magnetic flux, it will not induce voltage. Please see that if the phi is constant, DC magnet, no voltage will be induced in the coil. Even though magnetic flux is one, there should be a d by dt of phi should happen. That happens, as I told you many times the last 2-3 days. One is, I have a constant magnetic flux. I can move a coil. This is my coil. Coil is moving. Magnetic flux is constant. Phi is constant. The wire is moving. Then also d by dt of flux are cut. Then voltage will be induced in this coil. EMF will be generated. Or my wire is constant. Magnetic flux is varying. Sinusoidal square, it is time varying, correct? It is a time varying magnetic flux, but because AC current, automatically a voltage VEMF will be induced in the wire. This is the basic principle of AC voltage and magnetic field. Transformer induction motor works based on that. So since three phase in the magnetic flux is supplied by the stator, then in rotor, voltage is induced, three phase voltage is induced in the rotor, and since the rotor coil ends are short circuited, automatically current flow, three phase current flows. Okay, because of that, it creates again three phase magnetic flux. Please that I say that this is phi R rotor, correct? This is IR, rotor current. This is VR, rotor voltage. There are so you are getting. So the current generated due to each phase, I can say that IR is going to be IM into cos omega t. I can say that IB is going to be IM into cos omega t minus 120 degree, because you know that the stator coils are physically shifted by 120 degree, and the input voltage also, three-phase also, there's a phase of 120 degree phase shift is there. So because of that, the current induced in the rotor, and because the current flowing in this also will be same, three-phase will be shifted by 120 degree with respect to each phase. So this is the three-phase current going in the rotor. Okay. Now, because of that, again, we know that it creates a magnetic flux. I say phi R, phi B, and phi G, and they will be again 120 degree apart. You can say that, I can say that this magnetic flux phi R is K into IR T into cos omega T. Phi B is going to be, K is called magnetic constant, into IB into cos omega T minus 120 degree. Magnetic flux also, you can see that automatically phi G is going to be K into IG into cos omega T minus 240. Phase shift is going to be there. So the three voltages are induced in the rotor coil, whether it is a squirrel cage or wound rotor, and there will be a current will be flowing due to this induced this one magnetic flux. This magnetic flux is going to interact with the stator magnetic flux. I say the stator magnetic flux also, you have three-phase magnetic flux. They will then you are getting resultant magnetic flux or resultant. With that, this is going to interact and the magnetic torque is produced. That's how it works. Okay. So basically, we are going to get a torque at the induced torque. We call it induced torque in the rotor. Induced torque in the rotor. For example, before going further, we wanted to know, when we talk of induction motor, two more terminologies I wanted to talk. One is called as a slip. Correct? Slip. Other one is slip speed. Okay. We are going to see two things in this one. One is called slip. Other one is called slip speed.
Sir, I have a question. Can I ask if you allow me?
Definitely, definitely, please.
Professor, in the last class, you have taught us regarding synchronous motor. Okay. And you have taught us that three-phase current is provided in the stator, and a DC supply is provided to the rotor.
Correct.
And by aligning that, the rotor is chasing up the rotating magnetic field, and hence by that way synchronous motor works, right?
Sir? Correct. Yeah, correct. So, you are correct.
Yes, sir. So precisely what I got from that concept is that for starting a synchronous motor, we have to have a external DC supply to the rotor, right, sir?
Yes, yes.
Now, if we come to induction motor for time being, so here you are teaching us that we are providing three-phase like current to the rotor.
Yes.
And there is no external supply needed for the stator as well.
Rotor.
There is no external supply is needed for rotor, right, sir?
Yeah, correct. And the magnetic flux in the stator, which gives resultant, that is going to induce a voltage in the rotor coil.
Okay, so
that's why I say it is like a transformer. Transformer primary only you are giving voltage. Because of the primary voltage, there's a primary current. Because there's a primary magnetic field, that magnetic flux will cut the secondary coil. Here, secondary coil nothing but rotor. So that's why induction motor I started with the transformer.
Right, sir. So the question I want to ask precisely is that, like induction motor, hence induction motor is a better like evolved version of synchronous motor in that sense.
Yes, it is better. That is why it is used. You only one power supply. You don't need additional power supply, and construction is simple, correct, rugged, and it works similar to synchronous motor. It is a constant speed motor. Correct. It depends on supply frequency. Same. You are going to see the same equations. Almost same equation like what we are going to see, slightly modified. Correct. We are going to see new terms like slip speed, all these things. That's why I wanted to tell the new information to you.
Okay,
Sir,
sir.
one
Thank you.
question from my side also.
Yes,
Sorry
please.
if it's not part of the discussion, but in ICE engine we will have friction torque, right?
Yeah.
Usually we will not have that concept when we are talking about electric drivetrains. How do we account for mechanical friction in case of motors, sir?
No, so the power or torque generated by the magnetic flux interaction is called induced torque. We call it tau d in electrical. This is called induced torque at the rotor. Induced torque in the rotor, correct? This is created. This is called a starting point. Then you have, because of this, and there's a rotation. Rotor is rotating, correct? I say omega r. So T then because of this power, we can say the PD or P induced. This power is equal to induced torque, and due to what is the happens, we call this induced torque. But this torque is not going to be same as in the shaft. P shaft will be always lesser than induced torque. I can say that always, because there are other losses. In fact, today I am going to teach about that. What is the power generator? What are the losses? What is the final shaft power is coming? There are equations you can, for electric motor is there. We can talk about that. We are going to talk about that.
Thank you,
Good
sir.
thing you asked. Okay. Okay. Now that we are talking about that, so the torque generated in induction motor, the basic equation T equal to 3 divided by, we are talking about 3 phase, 2 pi ns multiplied by s into E2 square into R, take down this formula, and R2 square plus S into X2 whole square. Okay. Where the S is called a slip. S is called a slip. It will vary from 0 to 1. The value can vary from 0 to 1. And when the rotor is at standstill, that means you supply voltage to your rotor, stator, 3 phase, and it produces magnetic flux at time t equal to, the rotor still not yet started rotating. We call this rotor is at a standstill. Correct? Rotor is at standstill. You applied voltage to the stator coil, but rotor is not yet to start, because torque production, because of mechanical inertia, friction, all those things take some amount of time to accelerate. Because of that, we say that rotor is at standstill. When rotor is at standstill, the slip value is 1. When rotor speed, because I told you we have two speed. One is called the synchronous speed, speed of stator magnetic field, we call as this one. Then other one is called rotor speed, speed of rotor. Correct? Speed of rotor is always lesser than synchronous speed. Okay. That depends upon slip value. Correct? The slip, when slip is 1, the difference is maximum. When slip is 0, that means ns is equal to nr. This is rotor speed. Rotor which is kind of mechanically rotating. This is the synchronous speed of the magnetic field. Stator magnetic field. Both will never reach this one, but it can happen if you say there's no friction, all these things are there, but it never happens. The slip will be there. Because of that, the rotor speed is always lesser than the synchronous speed. Okay. So in this formula, this is the full formula for, suppose if somebody asks you to find out torque developed in 3-phase induction motor, the torque developed is 3 divided by 2 pi. 2 is a constant, 3 is a constant, pi is a constant. N is the synchronous speed. We know that ns equal to 120 f divided by p, Already we know that what we saw in the synchronous motor, 120 is a constant, F is the supply frequency, 50 Hz, 60 Hz, 100 Hz, whatever, and P is the number of poles. If these two number, automatically you can find out from this. Okay, once that is known and the slip value is known, then you will be able to find out what will be the motor speed. Okay, so the motor speed can be computed using this slip and slip equal to, correct? In fact, there are two things, slip and slip speed. Slip speed equal to ns minus nr. Correct? Already I told you nr is the actual rotor speed and ns is the synchronous magnetic field. Then slip s equal to, okay, slip s equal to ns minus nr divided by ns. Okay, this will vary from 0 to 1. Many times slip will be represented in percentage. In that case, what will happen is this will be multiplied by ns minus nr divided by ns, whole thing multiplied by 100 is slip in percentage. Okay, the slip in percentage decides, okay, what will be the shaft speed. Okay, slip going to decide. Okay, now when we talk about the induction motor, okay, as I told you that we can take up some simple problem and try to find out how to compute the slip speed and the rotor speed, slip percentage, everything. Correct. Another thing before going further, I want to talk about the torque versus speed curve of the induction motor. So this is the torque is in the y-axis, x-axis is the slip. First we'll talk about slip. Slip varies from 0 to 1. Okay. If you see the curve for induction motor torque curve, and it can vary sorry, this is 0, extremely sorry. This end is 0, this is 1. Slip varies from standstill means 1. Otherwise, let me clear this. You can. Slip equal to 1. Here it is 0. Slip varies from 0 to 1 to 0. Standstill to when the rotor catches with the synchronous speed. And both are equal. Rotor speed and synchronous speed of this one. We can say that my torque curve, if you see the torque curve of induction motor, this is around 0.2 slip. This is 0.5. Okay, I can say 0.5. And this is 1. This is 0.75. Okay. So the torque will be flat up to 50%. After that, slip, after that it start increasing. It peaks at 0.2. Maximum torque is generated when the slip value S equal to 0.2, then it will start dropping quickly. It drops quickly like this. This is the torque versus slip curve. Okay, and we can say that the peak maximum is 160%. Yes, please.
Sir, just one doubt. Why
Yeah,
in the
yes,
graph? Sir, am I audible?
Yeah, you are audible. Yes, please.
Sir, that x-axis, why we have to take from 1 to 0 for this graph?
Yeah, no. Because slip you can take anyway. But this slip varies from 1 to 0. Okay, so torque reaches maximum when it is 0.2. Generally, this is how they draw the curve. You can reverse also. You can do that. Means the torque becomes 0 when slip equal to 0. It reaches torque becomes 0 when slip equal to 0. That means NS is equal to rotor. Rotor is catching. That means there's no pulling power. Magnetically locked, then torque will not be produced in induction motor. There has to be a slip, and the maximum torque happens at a slip value of 0.2 in induction motor. That will be 160% of this one. Okay,
so it's the center of the x-axis. One more zero also is there, so that is what we are feeling some.
No, not zero. I want to put 0.5.
Okay, sir.
Right.
Now
it is, yeah. This is 0.5. I started writing 0.5, then I thought why I wrote below.
Okay.
Understood, sir.
Understood, sir.
Okay. Then another thing is maximum torque it can do is 160%. That peak torque. For example, if I say induction motor, 100 Newton meter is the normal torque, and you can get a maximum 160 Newton meter at slip of 0.2. Okay. So, and you can see that this is the another advantage of the electric motor. That's why it will compare IC engine. You can see that at 0, what is this? Slip equal to 1. Slip equal to 1 means the NR equal to 0. Correct? NR equal to 0. NS has some value. Correct? So that means rotor is not rotating. That is at standstill. We know that in all automobile, during starting, when I wanted to move the vehicle from this one, we say static friction. Correct? Static friction is maximum when the vehicle is not moving. That means engine is not moving, or the electric motor rotor is not moving. That time it develops maximum torque. You can see that. But in case of IC engine, the torque will be go something like this. Correct? So IC engine torque, this is the max torque at particular RPM. X-axis is one. You can see that at standstill, engine torque is 0. But in electric motor, it gives that almost maximum torque. Correct? Almost close to maximum torque. Okay, that is one of the advantage of the electric motor, that the speed graph itself you can understand that, which is not there in case of IC engine. So that's why we go for electric motor. Okay.
Sir,
yeah.
One more doubt.
Yeah, yes, please.
Sir, torque to speed or slip, sir? I think it is a speed. I think so, sir.
Which one?
The torque, the x-axis side is speed or slip, sir?
Slip. See, that's what I said. When slip equal to 1, you have the maximum torque. That is, it produces almost close to 10% torque. X-axis is slip, not speed.
What about the speed, sir? What about the speed, sir?
Speed curve I will draw later.
Right.
Okay. Okay. Then, if for example, I have an induction motor, correct? And it is run by F equal to 50 Hertz supply frequency, correct? And number of poles, P equal to 4. Number of poles equal to P equal to 4. And we can calculate synchronous speed. N, and it runs with a slip, correct? Slip equal to 0.5. It can anything. I told you slip can be 1 to 0. 0 very rare, but because rotor speed will not be same as stator rotating magnetic field, because rotor has a mass, there's a friction, as a Rauschen somebody asked, there will be friction, bearing friction, wind friction, all these things. That means the rotor will be lagging behind the speed, rotating magnetic field. NR will be always lesser than that. Way automatically there will be some slip will be there. Maybe 0.1, 0.05. Slip can be even 0.05 or 0.1, something like that. Even at no load condition, because the rotor mass itself, rotor magnetic field is trying to catch the rotating magnetic field, stator magnetic field, phi s. But that doesn't happen because rotor has a mass, bearing friction, wind, internally there's a cooling air is going in the motor. All this thing creates some of the friction. Due to that, the rotor speed is always lesser than stator. So automatically slip comes. Already we know slip equal to ns minus nr divided by ns into percentage. So slip will be there. Slip never becomes 0. Correct? It will be 0.05, 0.02 or 0.01, something like that. Okay. But it can go up to 1. 1 is that rotor is not rotating. Correct? When the starting condition, slip equal to 1. So now I can say that I can give any value, slip value, 0.2, 0.5, 1, something you automatically can find out. So NS equal to, we know that 120F divided by P. So 120 into 50 divided by 4, this is going to be 1500 RPM. So synchronous speed of the magnetic field, correct? This is called sync speed of the magnetic flux, NS. Okay. Already I given S equal to 0.5. We can find out NR, that is rotor speed. This is rotor speed, nothing but motor speed. You can say that rotor speed or shaft speed, NR equal to NS multiplied by 1 minus S. This is the formula. You can note down. So we know that 1500 into 1 minus S equal to 0.5 already given in this problem. So you can say that it is going to be 1500 into 0.5. So that means my rotor speed NR will be 750 RPM. Okay. So if same thing, if I say that my slip equal to 0.2, right? Slip increases when load increases. Please note that when the motor load increases, slip increases. When motor load reduces, no load condition, slip will be very small. So in that case, the rotor speed or motor speed will be close to synchronous speed. So if I say this one, automatically you know that it is going to the NR for slip equal to 0.2, it is going to be NS multiplied by 1 minus 0.2 is going to be 1500 multiplied by 0.8. Right? So if you compute, you can maybe 1500 multiplied by 0.8, 1200 RPM. So that means this is a light load condition. The motor may be running at 1200 RPM. Okay, depending upon. Okay, so this is how you compute. Then another thing we already talked about is that is slip speed. Correct? Slip speed is going to be NS minus NR divided by NS. Correct? So we say that NS is 1500 and for slip equal to 0.2, when S equal to 0.2, we know that the NR equal to 1200, just we computed. So that means 1200 divided by 1500. So then you will get the value, whatever the value you can compute. For example, I compute another value for example, slip equal to, right, 0.05. Please tell many times the motor will be running with less than 0.1. Most of the time there are chances. Okay, so slip is 0.5, not 5. Then NS already same 4-pole motor. This one we know that 1500. The NR is going to be 1500 multiple 1 minus 0.05 is going to be 1500 into 0.95, and this is going to be NR, rotor speed, or motor speed is going to be 1425 RPM. Right? So for this, the slip speed, if you wanted to compute the slip speed, it is going to be 2.5 hertz. If you compute 2.5 hertz. Okay. So this is few things I want to know.
Sir, one
yes,
question
please.
I want to ask,
Please.
Can we go to the previous slide, sir? Sorry.
Yeah. Yes, please.
Where we have no, just one more, sir, please.
Yeah.
One more slide back, sir. Okay. Sir, basically you have told that if slip increases, then the load will increase also, right, sir?
Yeah, slip increases because
load. Exactly, sir. So that means load is nothing but the torque produced by the motor. It has to be equal to the load, right? Then only it will be able to sustain it.
Yeah. Yes.
So, sir, here if we look at the graph, sir, basically if we are seeing that if the slip is decreasing, the load is increasing, torque is increasing, sir. I think that is not matching the theory that we have learned now. Are you getting a point, sir? What I meant to say is, if
Okay.
the slip increases, then torque load will increase. Load increase means the torque will also increase by the motor. But here we are seeing that if we are reducing the slip, then only torque is increasing. Is that it's not in sync with the logic that you have taught, sir? I'm sorry, just a question came to my mind, nothing else.
Yeah. No. See, because another thing also I just wanted to this one, the torque equation. If you see the torque equation, what we saw, correct? Here S means slip. Correct? In this equation, you can see that slip is part of the torque motor generated.
Yes.
Okay. So you can see that it is in the numerator as well as the denominator. In the denominator, it is S square. Right? You can say R2. In fact, I thought of explaining about the equivalent circuit. I will come back to that. Okay. Where R2 is called rotor resistance, X2 is called rotor reactance, and U2 is the rotor voltage, induced voltage, and S is the slip, and NS is the magnetic flux or synchronous speed of magnetic flux.
Okay, sir. So, but the thing is that, sir, this graph and the logic is not getting synced actually in that way.
Okay.
That's the only point I wanted to share.
Definitely. Your point is well taken.
Right.
We will look into basically the torque equation. Torque produced in the motor depends on slip also in case of induction motor. And the torque equation gives S square. In the numerator it is S. In the denominator it is you have S square term. Because of that behavior is coming.
Okay, sir.
We will come back to you. I got your this one. Definitely, I will explain to you.
Sure, sir. Sure.
Okay. So now we have seen this one, but the next thing I wanted to talk in case of the induction motor is in electric motor specifically. We are talking about equivalent circuit of the torque. How did you arrive the torque? Correct? Torque equation, when you talk about what you call as equivalent circuit of induction motor. IM. I already told you the induction motor can be compared as a transformer. Okay, so this is called what equivalent circuit. You can note down. So it has stator coil and rotor coil, and coil. Actually, even though coil is single part, it has resistance and inductance. So this is called as equivalent circuit of the coil, one coil, stator coil. Stator coil resistance is called as R1. This is called as X1, JX1, because it is imaginary part. That's why they put a JX1. Then small thing. This is a resistance. Sorry, this would be resistance, and there's a inductance. I will explain what it is. First, you can take the circuit. You call equivalent circuit of the okay. We are applying a voltage. Okay, I can say that V1. Okay, this is input voltage applied to the stator, and because of that, there's a current flow. I call it I1. Right, that is stator phase current. They call it. Because three phase, we are showing one phase, so it is called stator phase current. The current, because of this voltage applied across these two terminals, so there's a current flowing in the circuit coil. So this is equivalent circuit R1, and this is called stator. R1 is nothing but stator winding resistance. And X1 is called reactance. Winding, stator, winding, reactance. Because inductive effect. Okay. Then this current coming here, I1, it divides into two parts. One is called IM. The other one is called I2. I2, okay, you can note down, I2 is called rotor current referred to stator. Because we know the stator, we are not supplying any current. Actually, all the power is supplied from the, rotor. Stator induced voltage, current is induced. That current is produced due to magnetic flux created by the stator coil. That the magnetic flux is created depends upon the current I. That depends on, that's why it is called I2 is called as rotor current referred with respect to stator, and IM is called as magnetizing current. It is called as magnetizing current in the stator coil. Stator coil. Okay. Then here you have the voltage. This voltage we call as E1. Note down. This is the terminology we are using. This is called E1 is called an air gap voltage. Is called as air gap voltage. And now I2, this is I2, correct? This is IM. We know that I1 equal to IM plus I2. Okay, that is one thing. Then this is the standard. The rotor part I am drawing now. Okay, so please note that this is equal to a transformer, correct? So just to understanding purpose, a voltage is E1 is applied in the stator final, that is going to induce a voltage in the rotor. That voltage I call ER. The voltage induced here is called ER. This voltage in the stator coil, this represent, as I told you, that we imagine that this is a transformer. The magnetic, this is called magnetically coupling, correct? Magnetically coupled. Stator and rotor are magnetically, that means energy from the stator is supplied to rotor magnetically as a induced voltage. Because of this induced current, this voltage called rotor induced. ER is called as rotor induced voltage, due to the current supplied by the stator from the supply V1. Okay, then this is called as JXR. JXR is called as rotor reactance, because there is an inductor. Because again, rotor also in a coil means it is a resistance. This one, this is called as RR. RR is rotor resistance. The whole thing is called as equivalent circuit of induction motor. Okay, so it basically works on the basic principle of transformer. So now we have drawn this circuit, and this can be, there are two parts, and this can be, this equivalent circuit can be. Can I go to next page?
Sir, we are noting it down, sir, please.
Yeah, I can go to next slide. Okay, so now we can say that the equivalent circuit.
No, sir. Sir, we have to note down, sir, please.
Yeah,
Just 2 minutes, sir.
I am keeping. Once you are there, please tell me, then we will go to next. This is called as RC. Sorry, you can note down. This is called as JXM. RC is nothing but core loss. RC is referred to core loss resistance. Core loss resistance. Sometimes it is also called as copper loss resistance. Also called core loss. Generally, they term some books sometimes they say copper loss resistance, and JXM is called as magnetic reactance. We call magnetic reactance this part. Okay, so what I want to explain is you are supplying an input to the V1. Because of that, there's a current flowing inside the motor to stator and also rotor. Okay, so this is total. I1 is a total current. Some part of this total current supplied to stator winding is used for creating IM. IM is called magnetizing current, correct? So this is what going to create the stator magnetic field. All the current supplied from the power supply input voltage is not going to be converted into magnetic field. Only some part is I1, some part is used for creating magnetic flux. And to create magnetic flux, because coil has inductance as well as resistance, it becomes two parts. One is RC, while the other one is XM. This is reactance part, this is magnet being a coil. This current is used for creating magnetic flux. Now, the other part is I2. I2 is nothing but the rotor current which will be supplied to the rotor from the stator through magnetic coupling. I2 is nothing but magnetically this current is converted to magnetic flux in the between the coils, transferred to the rotor. Because of that, there's a voltage induced. I2 generates a magnetic flux. That because of that, in the rotor there's an induced voltage. This voltage, due to that, there's a current. We call I2. That is IR. IR is called a rotor current. Please note that rotor current is generated due to the input current only, because rotor doesn't have own power supply. Correct? Because you are supplying input voltage, a magnetic field is created stator. That magnetic field will be transferred between the two coils, magnetic coupling. Then your voltage ER, it is induced. ER is rotor induced voltage. This voltage divided by this impedance. We know that ER divided by ZR is called as IR. IR is rotor current. ER is induced voltage. That divided by ZR. ZR equal to, we know that it is noted RR square plus XR square, JXR square root. So that current is flowing. Where RR is nothing but rotor resistance and XR is rotor reactance. Okay. So I go to the next slide.
Sir, one basic doubt I have.
Yes, please.
Sir, when it comes to magnetic flux creation, means reactance plays a major role or resistance plays the major role, sir?
See, the magnetic field creation depends on the both combined. The magnetic field creation depends purely on how much current is flowing. Current only decides the magnetic flux strength. How much? So that is what going to decide a torque producer. Current, we know that this equation, correct? You can see that voltage divided by impedance, correct? Voltage divided by impedance is going to decide. See, IR, you take this one, induced voltage divided by ZR. In ZR equal to the real resistance square plus inductance square or reactance square.
Okay, sir.
Okay, but one thing what you have to know is the XL is proportional to F, supply frequency. It is not constant. We know that XL equal to 2 pi FL, correct? But R is constant, rho L by A. So if your supply frequency varies, the reactance will vary. Resistance never varies. Because we are supplying a voltage, AC voltage, for example, 50 hertz. I say 100 volts, 50 hertz, correct? In that case, resistance, the current due to resistance part is going to fix it. I say that my R equal 10 ohms, correct? Voltage equal to 100 volts. 100 divided by 10 is going to be 10 amps current. That is current due to resistive part. What about the reactance part? Reactance equal 2 pi FL, correct? That depends upon the frequency. Correct? If frequency 50 hertz, XL is something. If frequency 100 hertz, it is going to be different. If the frequency is 25 hertz, it is different. So the magnetic field creation is proportional to the impedance of the stator coil and also rotor coil. All are linked. That's what we are going to explain now. Correct?
Yes.
Final torque, current, all these things depends upon the Z combined effect of resistance from and reactance of stator as well as rotor coils.
Understood, sir.
Okay, thank you. Okay, now this is for this one. This circuit, equivalent circuit can be minimized like this. You can take this. This is called as minimized equivalent circuit. Whatever you saw. So you have this is R1, this is JX1. Please note that JX means it is imaginary part. It is a complex quantity. Impedance, that is a complex quantity. It has real part as well as imaginary part. Correct? Z equal to R plus JXL. Correct? JXL imaginary part, R is called real part. Together, it is a complex quantity. That is a complex quantity. Okay. So this is going to be, it's not going to vary. R part is going to be fixed. JXL will vary depending on the frequency. And also it is going to introduce what we call phase shift. That's why it's called imaginary part. Okay. So this part, this can be referred. Yes. Here we are giving input voltage. This is my I1 input current. This is called R1. R1 X1 is nothing but a stator, resistance and reactance. Hereafter in the for induction motor, wherever we say R1 X1 means this stator, reactance and resistance. IN is the current entering into the stator coil. That is divided into two parts. One is called as IM, magnetizing current, which flows in this is RC and this is JXM. Same terminology only. Only one thing is the I2 is called as rotor current and JX2 is the reactance of the rotor and R2 divided by S, correct, is called as rotor reactance with referred to stator. Why here you can see that in the previous this one I said here just R substitute rotor resistance, but in this case I put R2 divided by S, where S represents slip of the motor. Slip value vary from 1 to 0. That already you know. Okay. So here R1 is stator resistance per phase. Correct. We know the three phase. There are three coil. We are talking one coil. One coil with respect to rotor. And X1 is called as stator reactance per phase. Then R2 is rotor resistance referred to stator per phase. Because we are talking 3 phase, we are talking single phase. But that will apply for all 3. Then X2 is called as rotor reactance referred to stator phase. Okay. So this is for the final equivalent circuit. From this, we can always calculate this is my input voltage. So this is equivalent circuit of the motor. Okay. Now that we understood the equivalent circuit, all those things, and we'll look at how the power flow happens in induction motor. Somebody asked, that's what I said I will do. Power flow and losses. Losses in IM, induction motor. Okay. So you can see that it's like a big pipe, starting with a big pipe, correct? Here, power input, P in means input power supplied to induction motor can be calculated using this formula, Vt into IL into cos phi or cos theta, correct? Power factor, okay? So root 3 is, we are talking 3 phase, input to power equal to P input equal to root 3 to Vt is called terminal voltage, IL is the current supply, that is line current, cos phi is called power factor, cos into theta, theta value 30 degree, theta can vary from 0 to 90 degree, okay? When cos 90 equal to 1, that means power factor equal to 1. This is called as power factor. Cos theta is called as power factor in AC circuits. Power factor equal to 1 is better, correct? But a lower power factor is not good. But many times in inductive circuit, lower power can happen. Power factor can be less than 1. It can vary from 0.5, 0.6, 0.7. If you have inductive load, the power factor, please note down, the power factor PF, they call power factor, which is nothing but cos theta, where theta is called as phase angle between voltage and current. Phase angle between voltage and current. Voltage and current I is called as theta. Cos of that is called power factor. Power factor 1 is good. If I have a AC voltage, please take this one note down. If I have a AC voltage, say 200 to 200 volts, 50 hertz AC voltage connected to a resistive load or pure resistance, then I have a current. This I call V, this I call I equal to V by R, correct? In this case, the theta, which is called as phase angle, will be 0. That means what it means is, I can just draw, this is my input voltage, my input current also in phase. That means it also sinusoidal, it is in phase, there is no phase difference. This happens in resistive load. If I supply a AC voltage to resistive load, current and voltage is in phase, there is no phase shift, theta equal to 0, cos 0 equal to, you know that it is 1, correct? There is no phase shift. Maximum current cos theta equal to 0, power factor to 0. Generally, power factor, now if it is inductive load or capacitive load, power factor will not be 1. Correct? Cos theta will not be 1 because there will be a phase angle. There will be a phase shift. What is that phase shift? Already I told you for you to understand. This is my input voltage. If the inductive load, the current will be shifted something like this. So this angle 90 degree will be there. Correct? The current and pure inductance, that is called the theta. So cos theta and cos 90 equal to, you can see that it will become 0. Correct? Cos 90 equal to 0. That means that is called reactive power. Generally, it is not acceptable, but that happens if the pure inductance. But inductance itself, we know that motor coil also, it has a resistance also. That's why R1 plus J. Because of that only, the power factor value will be varying less than 1, 0 to 1, it will be varying depending upon the inductance value of the coil, motor coil. Correct? If more inductance, the power factor will be bad. It is not good. Okay, the power flow diagram you can note down, right? So the power flow diagram in motor, we are talking about the motor. So in this input power, the first power loss is going to be PSCL, where SCL means stator copper loss. Correct? So you can see that this big was there. Why? Now after this become less. Some power is lost. This much power is lost in through copper loss. Correct? That copper loss happens because of the power loss here. Correct? Here there are two, you can see that there are two resistance. Magnetization is RC, copper resistance is also. Here when current flows, I square loss we call it, because the power is wasted. The input power, some amount of power is wasted as a heat in R1 and also RC. Similarly, it is going to happen in the rotor also R2. Okay, so first thing is we are talking about stator coil power loss, which is called PSCL, first power. Next one is P core loss. P core loss. Okay, so P core loss happens in the magnetizing circuit. Correct? This is core loss. The R1 is copper loss. This is going to be copper loss. This is going to be core loss. Please note that again due to resistance of the magnetizing part. Okay, so this is going to be there. After that, you can see that now the input power is this much and it has reduced this much because of the losses. Next one is PRCL, where RCL means rotor copper loss. Okay, then you can see that again it is diminished. Power is gone, reduced. Some amount of power is wasted. Next important is P frictional losses, bearing losses, or all those things. Correct? The rotor is rotating, the support of bearings, any other frictional losses. Then because that power is still reduced. Okay. Now final loss is called what? P stay losses. Stay losses are generally due to airflow. Please note that in motor, one end of the motor, you have a fan which sucks the air. Because of the copper loss, all these losses going to generate heat in the motor. Stator winding, copper, the rotor winding, everywhere heat is generated. That heat to be cooled. So one end of the rotor side, the internal there will be a fan which sucks the air, and when air is flowing inside the motor, and it creates air resistance. That is called as stray losses or air losses. Any other losses. So this is the final P out. P out. P out equal to tau. Many books, torque is represented by not capital T, they represent by tau also. There is a tau load, that is load torque multiplied by omega m. Omega m r is nothing but omega r, rotor speed or motor speed. Motor shaft speed or rotor speed or motor speed multiplied by load torque is the final output delivered to the road. That is what available. So you can see that there are 1, 2, 3, 4, 5 losses happens. I gave this much input power. Finally, I am getting this much. Okay. This is what the power delivered to the, this is what they call power flow diagram. Note on this. If you are asked to draw the power flow diagram, you can draw this. Okay. So there are equations. I just will take another 5 minutes to complete this problem. As I told you, P input power can be calculated, correct, using the formula √3 into V5 into that input already we saw in the previous this one. I think I mentioned T also sometimes they say terminal voltage, sometimes they call it okay. There are two formula in this calculation to calculate this. One is called P in equal to √3 times VT into IL into cos theta. Otherwise, the other formula is P in can be computed using 3 into V5 into I1 into cos theta 1. Okay. So this is called a terminal voltage. This is called a line voltage. L means line voltage. This is the phase angle. √3 is a constant. Instead of that, if I talk of phase voltage, correct? Phase voltage, there are two voltages. If you talk about three phase, I have three phase coil connected. If you see what are three things, R, G, B, and neutral. 4 wires will be coming three phase voltage. If I measure voltage between neutral and the any phase, it is called as VT, terminal voltage. Terminal voltage is between neutral wire and any of the phase voltage. Okay. And if I measure voltage between two phases, it is called as V phase. That is phase to phase voltage or V phase. That means between any two phases measured voltage, that is called as phase voltage. If I measure voltage between neutral and any phase, it is called terminal voltage. If I use the terminal voltage under the current, line current, then I can use this formula to compute the input power supply by induction motor. If instead of the induced that input resistance, otherwise, if a phase voltage and stator current I1 under the stator phase angle is given in the problem, you can use this formula to calculate input power. Okay. Then in the so we will take this formula for further continuing. Right. I'll just take 5 minutes to close this. I know the time up. Some few formulas alone. Then we will tomorrow we'll see some problem solving for example.
Sorry to interrupt, sir. Can you please explain about the theta and theta 1 difference?
Yeah, the theta 1 is the phase angle between the terminal voltage and terminal current. And this one we are talking about theta 1. We are talking about rotor stator phase current with respect to phase. That is okay. So these values will be given in the problem. Okay, theta 1 or phi 1, VT IL or V phi I1 will be given. Then automatically you can calculate. Right now, for the problem, what you are going to right now, you can forget about this. We will use this formula for continuing further. P in equal to we are given V phase voltage and I1 is the stator current and the theta 1 is given, phase angle is given. Then using the formula, input power supply to voltage the can be computed. Then next one is to find out I1, because in this formula you have I1. I1 to compute you need what you call as Z equivalent. That is equivalent impedance of the motor can be written with as R1 plus JX1. Take this formula, then tomorrow we'll solve some problem, you will understand. Plus RC is in parallel with JXM, which is in parallel with R2 divided by S plus JX2. Correct? Please see that there are three terms. This is first term, second, third, fourth term are in parallel. This symbol means they are in parallel. Correct? So we will find it. Then once you compute this, so what do you need? R1, X1, RC, and XM, and R2, slip, and X2 are these parameters given. Automatically you can compute J equivalent. In the problem you will be given, from that you can compute. One that is known, then you can compute I1. Correct? I1 we need to compute. I1 can be computed using V5 phase voltage divided by Z equivalent. correct? Generally, it will be a magnitude with an angle. When you compute this, you will get theta 1. Theta 1 is the phase difference between the voltage and current. I told you, if I supply a AC voltage and being inductive circuit, automatically that way phase shift would be there. This is my voltage, correct? V phase. This is my current, is I1. The difference is theta 1. Phase angle between this one is called as theta 1. Theta 1 depends. Please see that theta 1 depends upon Z. Z in this R1, RC, R2 will be constant, but XM, X2, X1 will vary depending upon frequency. Correct? For a given inductance value, you know that it is 2 pi FL. If depending on FL value, it will change. So that's why the phase angle changes with respect to inductance value and also the frequency. Okay, so this is what the phi 1. The phi 1 can be, you will get, once you calculate V5 is given, Z equivalent if you compute, from that you can call I1. I1 consists of two parts. It is a complex quantity, correct? It will have real and this one, and we convert to this one from complex to polar form, you will get I1 plus angle. That angle is nothing but phase difference between the input voltage and input this current. Input current is stator current. V5 is the input voltage, this one. So you can find out from this. So once that is known, correct, we can write this. Okay. Then next thing is just 2 minutes. I don't want to take more time. Sorry. Next one is called PAG. Correct. Already we saw that this equivalent circuit. Okay. We are talking about this one. PAG. PAG is called as air gap power. PAG means air gap. Correct? Power in the air gap. Okay, is nothing but P in. I will explain tomorrow. Just take the formula alone. PSCL minus P core. Okay, PSCL equal to 3 into I1 square into R1. R1 is the stator resistance. I1 is the current flowing inside the stator. 3 is a constant. You can compute like this. Then, so we can say PAG equal to 3 into I2 square. You can write like this into R2 divided by S, where S equal to slip. Okay. And you can write I2 equal to IR divided by RR divided by S. Sorry, this is IR. Very sorry, very smart. IR equal to ER, rotor induced voltage divided by RR divided by XR. JXR. Okay, this can be written as ER divided by RR divided by S plus JS XR naught. I will explain tomorrow. This is IR. From IR, we can find out I2. I2 equal to IR divided by AEF, where AEF is called as effective turn ratio. That will be given. Effective turn ratio. Effective turn TURN ratio. Okay. Once that is known, then you can call PAG equal to, this is the formula you can know. PSCL, you know, PAG is given like this. Now, the next one is called PCNV. CNV means converted, power converted. Converted is short form is power converted from electrical to this one is called a P convert is PAG minus PRCL. Okay, PRCL equal to 3 into I2 square into R, and P convert. So P convert can be written as 1 minus S into PAG, another formula. Okay, so finally, if I want to find out the P output of the motor is nothing but P convert minus P, F and W frictional wind plus P miscellaneous also. Okay. So lastly, the induced torque tau equal to P convert divided by omega m. Omega, this is subscript m, okay, can be written as 1 minus S into PAG divided by 1 minus S into omega synchronous speed, omega sync speed. We know NS can be reduced. So this and this goes away. So you can say that induced torque equal to PAG divided by WS sync speed. I stop here. Sorry for taking a little time. Tomorrow we'll do some problem because you can expect some problem from this for your midsum exam as well. We'll do 1 or 2 problems to solve this so that you will understand better understanding how the input AC power is converted to mechanical power. PAG is the mechanical output power available in the shaft. That is proportional to the AG means air gap. See, from stator you are supplying voltage, magnetic flux is created. That magnetic flux is transferred to the rotor through the air gap, because between the rotor and stator there is an air gap. That how much power is transferred, that power only is converted into mechanical torque, not all the input power. So other copper also finally we are going to get shaft power, which is nothing but P output, which is always lesser than the generated power. I stop here. Please give your attendance. Tomorrow we can see some problems in this 1 or 2 problems. Then we will go ahead with advantages of the synchronous motor compared to this one. Benefits, all those things you can see. Yes,
Sir,
please.
can you please go back to the previous slide, sir? Just I will. Yeah, thank you, sir. Thank you.
No issue, no issue.
Sir, can you please, like I2 equal to IR by coefficient, right? Like
I2 equal, where is it?
the last
A
bottom one.
effective, A effective.
A effective, okay.
Subscript effective. They call effective turn ratio or the rotor winding, all those things that will be given by the manufacturer, or they will be given the value. If it is one that is known, then IR you can compute using this formula, which is talks about resistance of rotor and inductance of the rotor. XR is this one that is known, automatically you can find IR, that is rotor current. From one to rotor current, I2 can be computed using one of the formula. We'll see whether alternate formula also is there, then we can do that tomorrow.
Okay, sir. Yeah, sure. Thank you, sir.
Sorry. Okay, please give your attendance before leaving. Thank you very much. See you by tomorrow.
Thank you, sir.
Okay.
Thank you, sir.
Thank you.
Thank you, sir.